Now, in this video, we'll be talking about a molecule, and everybody knows what a molecule is. And if we see onto the planet, uh, we generally see atoms. We don't generally find atoms on the planet, except we can find them on the lower portion of atmosphere in the form of inert gases. Otherwise, the atoms they join with other atoms and they make molecules, and they may make complex molecules, and they can make compounds. We can have situations where same kinds of atoms join together and form a material in the form of a compound. And it is also equally plausible that we have things out there where atoms of different elements are joined together with very complex structures. So so to say, the question that arises in our mind immediately is that okay, atoms when atoms combine, they form molecules. Now the question is, what's the reason of that? What's the reason of that attraction? What's the reason that atoms are held together by some forces? And certainly the intuition here is here to make use of the quantum mechanical approach of at least getting some idea about the bonding of these atoms, that how these atoms make complex molecules, how they make simple molecules. So this intuition is equally forcing both physicists as well as chemists to have the explanation of formation of these molecules. And to be precise here, the ability of the quantum theory to explain this bonding with no special assumptions should be the point of view to be put in place. Now, what we have in a molecule is we generally say a bond. We talk about a bond, and we call it a molecular bond. And this bond is there because of electric forces. And it's because of these electric forces that molecules are formed. And a molecule in itself is electrically neutral group of atoms that are held together strongly enough to behave as a single particle. So you have different atoms, they are bound together, and they try to behave as a single particle. And uh, for the case of reason, if we talk about two hydrogen atoms, if I have a hydrogen atom and I have another hydrogen atom, and and uh, and the water molecule, the two hydrogen atoms, they always exist in the water molecule with an addition of one oxygen. So we have hydrogen, and we have oxygen. And what they do, they make a water molecule. Now, if one of the atoms of this molecule is removed, this is hydrogen, and this is oxygen. And if we are able to separate down one of the atoms from this molecule, what happens is that it becomes the result is a molecule of a different kind with different properties, and that's what makes it very strange. That's what makes it plausible. That's what makes it beautiful. but complex mathematically. So if you remove an atom from this water molecule, there is a race for another molecule, and the properties of that molecule will be different than that of the properties of the water molecule that we have. And at the same time, this a molecule exists because its energy is less than that of separate atoms. So if I have atom A and atom B, uh, uh, I have a molecule of AB, and this molecule of AB is formed only because they are able to generate an overall energy which is less than that of the independent energy of A and B. And now, if we have the interaction among certain groups of atoms, this interaction certainly reduces the total energy between this A and B. And let us see what happens when two atoms are brought together. So what we have is certainly we have the we have the uh, the electrostatic force that's existing between these two atoms, because each atom has a nucleus and they have electrons roaming around them. So if we take an example of bringing close two atoms to the very extreme, to the very kinds of situations that I want to talk about here. Now, the first thing I would like to go with is that that if we have one or more pair of electrons, and they are shared by the two atoms. Suppose it has an electron, and they share these electrons between each other. What we say that there is a bond between these two atoms, and we call this bond as covalent bond. Now, as these electrons circulate between their atoms, okay, this is for the sake of arguments. We don't know where electrons are, but there are only probabilities of electron being anywhere around the nucleus. Now, what they do is they spend more time between the atoms than elsewhere. Okay, they are with their nucleus. They are with their nucleuses, and which produces an alternative force. Now, taking an example of this, assuming this is hydrogen, the hydrogen molecule, here I'm talking about. Now whose electrons belong to both protons, and the attractive force of the electrons exert on protons is more than enough to counterbalance the direct repulsion of the nucleus. So we have the situation of repulsive force between the nuclei because they are both positively charged. But the systemization of electrons is such that the overall attractive force, that's by virtue of the electron cloud, and the force that's there between these two nucleuses, the attractive force, it trespasses the repulsive force between the two nucleuses. And now, if the protons are too close together, now if we bring them close together, and their repulsion becomes dominant, then if the protons are too close, that I'm saying, then the molecule is not stable in that case. It is unstable because the force of repulsion between the nucleuses may overcome the stability of these two hydrogen atoms. Now, the balance between attractive, what we have here is we have electrostatic attractive force and we have repulsive force. And these forces occur. They occur at a separation of nearly 7.4 into 10 to the power of minus 11 meter. And the total energy of this H2 molecule that we have, this comes out to be nearly 4.5 electron volts. Hence, what we have to do is we have to subject 4.5 electron volts of energy to this hydrogen molecule. This much of work I have to do. The two hydrogen atoms will be apart from each other. All I have to do is to give an energy of 4.5 electron volts. So you will have independent hydrogen atoms. So to say, what it reveals is that if I make a comparison of this kind of arrangement for this molecule with the atom itself, if I make a comparison with the atom itself, for hydrogen atom, if I take the case, for hydrogen atom, and we understand that we have to provide 13.6 electron volts of energy for the electron to be completely outside the regime of this hydrogen atom. So what do we get here is here that the energies that are involved for molecules, if we make the comparison between the molecule of hydrogens, two hydrogen atoms, and a hydrogen atom, it certainly seems that we have to use very small energy in comparison to the hydrogen atom. And this is the fact that we need very less energy to break the molecules instead of atoms. So to break molecules is a little bit, it's a simple job than that of breaking atoms, getting electrons out of these atoms. Now, so to say, so what we have had here was an assumption that you have a kind of sharing of electrons between these two hydrogen atoms, and what we call it as the covalent bond, and this kind of bonding is called as covalent bond. And so to say is, if we talk about another situation where we have an atom, and this atom has electron, and it loses its electron, and this electron is taken by some another atom who is in need of an electron. Now, so to say, if I will take an example of, generally the example of sodium chloride is taken in this case. What we have sodium, and its atomic number is 11, and I will just draw its outermost shell. It has one electron. And so to say I have chlorine, and I will just draw its outermost shell, and it has 6 electrons, 6 or 8 electrons. It has 8 electrons. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Now, what am I trying to say here is that we have chlorine with I don't remember its atomic number. It must have 5. Must have 7 electrons. Yeah, it must have 7 electrons in its outermost shell. 1, 2, 3, 4, 5, 6, and 7. And it has just 1 electron. Then its inner orbits are complete, and the inner orbits of this chlorine are also complete. So to say, the instability of this atom is because its octet is not complete. Its outermost shell is not having the complete set of electrons that it needs. It must have 8 electrons in its shell. And so to say about the chlorine has a lot of electrons in its valence shell, but it lacks 1 electron to be extremely stable. So in this kind of situation, When some work is done, what can be expected is that we have a bond. A bond can exist between this sodium and this chlorine ion, and and this bond will not be between Na and Cl. This will be between Na positive and Cl negative. And and this bond is called as ionic bond. This kind of bond is called as ionic bond, and that's the reality of it. And and the crystals of rock salt, they are basically the aggregates of this sodium and chlorine ions, which although always arranged in certain definite structures, they do not pair off into the molecules consisting of Na positive and Cl negative. That's not the case. Rock salt crystals may have any size and shape. They are always equal in number. The number of Na positives is equal to the number of Cl negative ions in the rock salt. So that the formula that we have, NaCl, that we talk, it correctly represents its composition. And if we have molten NaCl, it also consists of Na positive and Cl negative ions, and these ions form molecules rather than crystals only in the gaseous state. So ionic bond is a result of stabilizing the energies of the two atoms, and it all depends. It's behaving like this one needs a lot of electrons, this one needs just one. So to make him stable, it would like to lose its electron, and it loses its electron, and it has all the 8 electrons it wants in its outer orbit, and sodium also has its octet complete. So to say, in hydrogen, the bond is purely covalent that we talked about. In H2 case, the bond between these two hydrogen atoms is completely covalent, and in case of sodium chloride, NaCl, it's purely ionic. Now, in many molecules, an interaction type, we can have intermediate types of bond, and these bonds can occur in which the atoms share electrons to an unequal extent. So to say, for example, if I take an example of hydrogen chloride molecule, where Cl atom attracts the shared electron. It attracts the shared electrons more strongly than hydrogen atom. Right? So to say here, what we say is that the ionic bond, as an extreme case of the covalent bond, we have this is an ionic bond, but its basis is a covalent bond. And when we have a situation when there is no bond at all between the two atoms, and the reasons for that is when the electron structures of the two atoms overlap, the structure of the two atoms overlap, and they constitute a single system. And according to exclusion principle, no two electrons in such a system can exist in the same quantum state that we talked about when we talked about Pauli's exclusion principle. Now, if some of the interacting electrons are forced into higher energy states, then what they does is they are occupied in separate atoms, and the system may have more energy than before, and that system will be unstable system. You won't have any stability, as there was a case of covalent bonding or the case of ionic bonding. And the system in that case will be unstable when you will force the two atoms to overlap so that their wave functions overlap. Now, even when the exclusion principle can be obeyed, with no increase in energy, there will be an electric repulsive force between various electrons. And this is much less, this is not that much important factor than that of exclusion principle that prohibits them to have the same quantum state. So here I would like to stop, and then we'll have the mechanism.